created by MindSticks Foundation Trust.
Hello, students, and welcome. Today, we're diving into a fascinating explainer on the chemical properties of carbon compounds. We'll be looking at four main things today. First up, combustion, then oxidation. Third, we'll look at addition and substitution reactions. And finally, we'll put the spotlight on two superstars, ethanol and ethoic acid.
Right, let's jump right into part one, combustion.
So what exactly happens when carbon compounds burn? Well, that's what we scientifically call combustion. Now take a look at the clear difference here. Saturated carbon compounds, they generally burn with a really clean, bright blue flame. And why is that? It's because they've got this perfectly balanced proportion of carbon and hydrogen. But on the flip side, unsaturated compounds have a much higher proportion of carbon. Because of this, oxygen actually struggles to burn it all completely, so it leaves behind these unburnt carbon particles that glow, giving off a yellow, super sooty flame. Now, let's apply this to something you see every day. Think about the gas stove in your kitchen. The fuel that comes through your pipeline or cylinder is designed to give you that nice, clean blue flame. But have you ever noticed the bottom of your cooking vessels getting coated in thick black soot? If you see that, it literally means the air inlets on your burner are choked up. The oxygen is blocked, forcing incomplete combustion. And you know what that means? You're wasting precious fuel. So pro tip here, keep those stove inlets clean to make sure you get complete combustion. Moving smoothly along, let's look at number 2, oxidation. Now, we know burning is a very rapid type of oxidation, but sometimes we want to see how carbon compounds mix with oxygen in a much more controlled way, like in a lab. To force this to happen, we use these special chemical donors called oxidants or oxidizing agents. Potassium permanganate and potassium dichromate are really common examples. Think of them as very generous chemical friends. They're powerful substances that happily hand over their oxygen to other carbon compounds. Look closely at this chemical equation here. We are actively transforming ethanol into ethanoic acid. How? By dropping in our oxidizing agent, alkaline potassium permanganate. Now, picture this in the laboratory. As you add the potassium permanganate drop by drop, you'd actually see its bright pink color just disappear. It's kind of like magic, but it's just chemistry. It vanishes because the chemical is being used up. It's literally giving its oxygen away. It only stays pink once every last drop of the ethanol has been completely oxidized.
All right, on to part 3, addition and substitution reactions.
These next reactions are absolutely fascinating because they show us exactly how molecules physically transform. Let's start with addition reactions. Here, unsaturated compounds, remember, those are the ones with double bonds, react with a substance like tincture iodine. Those double bonds literally snap open to add the iodine atoms right into the structure. And when that happens, the reddish-brown color of the iodine completely vanishes. It just decolorizes. So looking at this table of fatty acids from our text, ask yourself, which of these contain a multiple bond and will make that iodine color disappear? It's a brilliant, highly visual test for detecting those invisible double bonds. And here is a huge, everyday industrial application of an addition reaction, the hydrogenation of vegetable oils. We take healthy, liquid, unsaturated vegetable oils, and we literally add hydrogen to them, using a metal catalyst like nickel or platinum to speed things up. This process forces those double bonds to break, saturating the carbon chains, which turns the liquid oil into solid Vanaspati ghee. But, our texts do remind us, while unsaturated fats are healthy for us, these saturated fats made through hydrogenation, they are unfortunately quite harmful to our health. On the flip side, let's look at substitution reactions. Saturated hydrocarbons have very strong single bonds, so they're usually quite inert. They really don't like to react with things. But if you put them in direct sunlight, boom! They will react rapidly with chlorine. Just look at this sequence. You can see the chlorine atoms literally stepping in to replace or substitute the hydrogen atoms in methane one by one. A hydrogen leaves, a chlorine takes its spot, and you end up with a totally new set of products. Finally, section 4. Let's shine a spotlight on two very important chemicals, ethanol and ethoic acid. I guarantee you've encountered both of these in your house without even realizing the chemistry behind them. Let's talk about ethanol first. It's a highly versatile, totally colorless liquid at room temperature, and it boils at 78 degrees Celsius. What's amazing is that it's perfectly soluble in water in absolutely all proportions. And because it's such a fantastic solvent, it's a key ingredient in medicines like tincture iodine, cough syrups, and tonics. Also, because it burns so incredibly cleanly, some countries actually blend it with petrol to create a highly efficient, much cleaner fuel that we call gasohol. But listen up, because as your teacher, I really must highlight a very strict warning from our textbook. While dilute ethanol is consumed socially in various parts of the world, drinking pure absolute alcohol is incredibly dangerous. It severely harms your physiological processes and totally messes with your central nervous system. Like the text clearly states, consuming even a tiny quantity of pure ethanol can absolutely be lethal. So please, it's a powerful chemical that has to be treated with the utmost respect and caution.
Now, what about its chemical reactivity? Well, if we go to the lab and mix liquid ethanol with a superreactive metal like sodium, you get a very vigorous reaction. It rapidly liberates hydrogen gas and forms a salt called sodium ethoxide. If you do this in a simple test tube, the release of those hydrogen gas bubbles is so intense that the little solid pieces of sodium literally look like they're aggressively dancing around on the surface of the liquid. It's really cool to watch.
Another incredibly vital reaction to know is dehydration. And just like it sounds, dehydration means we're removing water. If we carefully heat ethanol with an excess of concentrated sulfuric acid at exactly 170 degrees Celsius, that acid acts as a powerful dehydrating agent. It forcibly yanks one entire water molecule right out of the ethanol, leaving us with an unsaturated compound called ethene.
All right, let's shift gears to ethanoic acid. You almost certainly know it by its much more common household name, acetic acid. A simple 5 to 8% dilute solution of this in water is exactly what vinegar is. Yes, the same vinegar used to preserve the pickles in your kitchen. But the pure state is what's truly fascinating. Pure ethanoic acid has a melting point of just 17 degrees Celsius. That means in cold winter climates, it freezes so easily that it turns solid and looks just like a block of ice. Because of that, chemists gave it the very cool name glacial acetic acid.
If we want to verify these properties in the lab, we do a very simple litmus test. We just take a strip of blue litmus paper and place it on a clean glazed tile. Then, using a glass rod, we drop just one single drop of dilute ethanoic acid onto the paper. Instantly, right before your eyes, that blue litmus strip will turn a bright, vivid red, confidently proving its acidic nature.
As we wrap up today's explainer, I want you to just sit back and really think about this for a second. How is it that these totally invisible, microscopic single and double bonds inside carbon molecules fundamentally dictate literally everything around us? I mean, from the fuel we burn to cook our dinners to the cough syrups in our medicine cabinets, right down to the vinegar on our dining tables, the chemistry of carbon isn't just textbook stuff. It is literally the chemistry of our daily lives. Keep observing the wonderful science happening all around you, and I will see you in our next lesson.